Okay, so welcome everyone to the first colloquium of this year. And we have a great pleasure and honor to have Ofek with us. Before I introduce him, I want to say a few words about how the colloquium is going to be this year. So last year, the Corona situation took us off guard and we didn't have many colloquiums in the second semester. This year, together with Amos, we thought what we should do. And the first thing is there has been an organization of a joint organization of all the physics departments in Israel to have a joint colloquium. And the upshot here is that we can invite speakers really of the top tier in the world to give colloquiums, and we have an amazing list of speakers. Everyone who was invited said yes. So there's a lot to look forward. The bad news is that these colloquiums will not be in our regular time at quarter to 11, but at 4 p.m. We'll have before that 5 minutes of meetings in breakout rooms, and then the colloquium will start. So this will happen once every 2 weeks. Next week will be the first time we have this Israeli physics colloquium. And the rest of the weeks, we have a Bar-Ilan colloquium where we'll also have speakers from abroad, but also we'll take the opportunity to get to know researchers from Bar-Ilan that we haven't heard from for a while. Yeah, the second thing is, as you noticed, we had a breakout room before the talk, and I think this is something we're missing, the contact with other people. So we're going to do this every week. We'll open the Zoom at 10:30, and we welcome you to come and say hello to each other. And we will open a few breakout rooms so that so that you can talk in smaller groups. And that's all the introduction. And now let me introduce Ofek. So Ofek is is one of our last and greatest star recruits of the department. Ofek did 2 undergraduate degrees in the Technion in physics and computer science, and then did his master and PhD in Jerusalem. And then he went to Hanover and later to Rochester, New York, to join the LIGO collaboration and look for gravitational waves. And I think at the time when Ofek left there, the feeling between most physicists is that gravitational waves, I think we felt about it like we feel now about dark matter, that it's very important, it's in the forefront of physics, but it's probably never going to be found, it's just too hard. And we were proven wrong, and maybe Ofek can tell us about it. So Ofek, thank you very much for willing to give this first talk, and thank you all for joining us.
Thank you, Yoni, for the introduction and for the invitation. It is an honor to open the colloquia session and season and the school year at Bar-Ilan. I would also like to take this point to announce that we're starting the astrophysics regular seminars this semester. They'll be held Thursday at 5:00 p.m. to allow for American East and West Coast time participants. We already have scheduled talks every Thursday this semester, so you're all welcome to join. Yoni asked me to give this colloquium, the first of the year, a festive atmosphere, to make it kind of an occasion. And luckily, I didn't have to work very hard. The Swedish Royal Academy chipped in making this a very festive occasion indeed. And we can start by congratulating the winners, the laureates of the Nobel Prize in Physics for this year, Roger Penrose, Reinhard Genzel, and Andrea Ghez. The 3 of them have been major contributors to the field of astrophysics, in particular to black holes in astrophysics. They have really been the people before gravitational waves to bring black holes out of the mathematical notebooks and into our everyday astrophysical experience and observation, into our reality. Roger Penrose here is cited for the discovery that black hole formation is a generic prediction. So it's not just a mathematical curiosity. It's not a measure zero solution to the equations. It's something that can happen generically. And Genzel and Guess have been the first to observe what is convincing evidence of a black hole. We have the full citation here, these are images from the Nobel Committee announcement. On the left, we have an example of Penrose's contribution. In the field of general relativity, we have space-time. Space here is represented by the plane going left and right, forward and into the screen. And the up direction is traditionally representative of time, going forward up in time. And what Penrose established was that if enough matter collapses into a sufficiently small circumference or area, it would collapse into a black hole generically. That is, once a particular mathematical property is satisfied by the matter on a certain surface, it becomes an outer trapped surface. That is, light rays would be focused inwards from that surface and no longer diverging outwards. Then it is a mathematical theorem by him that eventually a singularity would form. And you don't need what people thought of up until that point, special demands for spherical symmetry or axial symmetry or particular vacuum solutions. It's not a special thing that happens. It happens under very general conditions. And once it happens under very general conditions, then we really believe that it does happen in the universe. It's not a specific thing, it's a very generic thing. It actually becomes, if you want, an attractor of the differential equations, which are Einstein's equations in general relativity. Black holes should generically form and populate the universe. Convincing observations of such an object was found in the center of our galaxy. Sagittarius A star, represented here in an X, is an object that we have not yet seen directly with any telescope, but it's a black hole. We don't expect to see it directly. But these teams have followed stars orbiting around the center of our galaxy. They've traced several tens of stars in very close orbits. Because the mass is so large, these orbits are actually very fast, and they've managed to complete revolutions of some of them. This one, for example, has a period of 16 years, S2, a very eccentric orbit. It's been followed for a long time, and it matches the predictions of, in this case, a Keplerian orbit relevant to surround a mass of about 4 million solar masses. So an object 4 million times as heavy as our sun, yet we do not see it. And we see that these objects, the star is orbiting it very, very closely. So 4 million times the mass of the sun, as a black hole, would take something like 12 million kilometers in radius. And we can follow these stars about getting as close as about 1,000 million kilometers, or 1 billion kilometers. So there's about a factor of a few hundred or 1,000 relevant in the ratio between how close the star gets to this black hole or to this object and how close it possibly could get to this black hole. In our solar system, even though the mass is much smaller of the central object, the sun, we know that the closest objects orbit very, very far away. Mercury and Venus and the Earth orbit astronomical units away. In this case, we have an object that comes as close as a few astronomical units. So this whole orbit can be positioned within the solar system, but not with the sun in between, in the middle, but with a 4 million solar mass object in the middle. This is considered very, very strong evidence for an object that is very, very heavy. We don't know of any star that could be so heavy, of any object that could be so small and heavy. And dark, the best guess we have for what it is a black hole. And now this is with following observations of other gravitational waves, confirming black holes from closer compactness ratio, so closer to the event horizon than this factor of 100 to 1,000. The committee has now approved of that and confirmed it with granting the award for proving that this object probably is a black hole.
Ofek?
Yes.
Yes, may I ask you a question? Why the black hole Sagittarius is not on the axis of the ellipse?
There is a tilt.
I have to see where this particular committee-produced graph comes from. But I should say an interesting thing that was only discovered this year and published in April. I mentioned that this orbit that Getz and Genzel found was a Keplerian orbit. In April, they announced also that they have the first non-Keplerian corrections to this orbit. They found precession of the perihelion, or in this case, periastron of this object. So we know perihelion precession to be an effect of general relativity, calculated by Einstein in 1915 for Mercury and confirmed for Mercury. It's a very small effect, so it's a sub-dominant effect to the Keplerian orbit. But now this orbit as well was confirmed to show this perihelion precession effect. Why is that not an axis? It's second 2D prediction of a 3D orbit. Okay. And I see also an answer about the Earth observation direction. Okay. So this is a great achievement, and the Nobel Committee, of course, confirmed this and granted it its due credit. But for us in gravitational waves, this is the before picture. This is what was known about black holes and observationally gathered as evidence for black holes before gravitational waves were found. It left many open questions, or some of them still are open, but this map of our knowledge can be basically summed up by what happens to stars and how do massive stars evolve. This is a very rough representation of possible fates of stars by mass. Stars begin on the main sequence. If they're of low mass, they will end their lives as white dwarfs. Either they're originally red dwarf small stars and they'll just shed away their warmth and slowly cool off into a white dwarf. Or for a star like our sun, it will go through a red giant phase and then end up as a white dwarf. Higher mass stars will go into hypergiant phases, evolve into much more spectacular astrophysical events such as supernovae. And then there's a split as well between those who are very high mass, enough to go supernova, but not enough to turn into a black hole, or on the other hand, low enough to sustain a remnant neutron star or pulsar. Or if they're even heavier than the highest possible mass for a neutron star, then they'll end up as a black hole. We don't exactly know the limit between neutron stars and black holes. We think there might be a mass gap between those two. We expect neutron stars, depending on the equations of state, which we do not know, to go up to about 3 solar masses. We have seen black holes starting from about 5 solar masses. In between, we don't know exactly where the limit is or what type of objects can be found. We also expect black holes to merge with each other, at least that's a mathematical possibility. And we expect neutron stars to merge with each other. When neutron stars merge with each other, they will most likely overflow the mass limit for a stable neutron star remnant and also turn into a black hole. So this is kind of the map of the objects we expect to be discussing for stellar mass black holes. I'll remind you that the Getz and Genzel black hole at the middle of our galaxy is not stellar mass. It's 4 million solar masses. But this is kind of the playground. The objects we kind of expected to find and where we were looking for them. Put on this mass plot, here mass is on the left vertical axis. There's no meaning for the horizontal axis. It's just an artistic layout. We have an assembly of the objects that were found as stellar remnants with traditional electromagnetic methods. We have neutron stars at the bottom. Neutron stars are very easy to spot because, or more easy to spot because pulsars emit pulses of radiation we can find. Black holes are slightly more difficult. We usually find them either because they're in binary systems and have companions, which we can see, or because they have accretion disks, which themselves radiate away energy that we can see. And we have here this kind of gap we were talking about, where we see most neutron stars clumped somewhere between 1 and 2 solar masses. We have stellar mass black holes starting to build up from around 5-ish. And we have very, very few wanderers or extreme cases of high mass neutron stars kind of straddling the 2 and a little, maybe 2.5 solar mass region, and maybe one black hole dipping a little below 5. Some objects we don't even know what they are in this mass gaps between 2 and 5. We also have an upper mass gap after above 20-something solar masses and leading up all the way to the 4 billion solar mass black hole, which we have in the center of our galaxy. So we have a very large range of masses to fill up and to populate with observations, which are hard to make, at least for black holes. When they're on their own, you typically don't see them. I saw some activity in the chat. Yoni, should I answer any of that? No.
No, they answered themselves. Asaf was answering a few questions there.
Excellent. So this is the before picture. Again, these objects we believe to exist by the new Nobel laureates' predictions and observations, electromagnetic pulsars, which we could find in other methods. This is the picture currently published with gravitational waves. So we have many more objects here in blue. Of course, in gravitational waves, so far we only detect mergers of binary systems. So all of these black holes come in triples. There are 2 constituent black holes which merge to form a third. And typically the mass of the third is just under the sum of their masses, because some mass 1 to 5 or 6 solar masses in these cases radiate away as gravitational waves, energy carried away from the system.
Ofek.
We also have systems of neutron stars merging. The one here on the right is gravitational wave event 170817, so August of 2017. The first binary neutron star merger seen and confirmed. It was seen not only with gravitational waves, but with a plethora of electromagnetic spectra observations, so we know exactly what happened. We don't know what the end result of that was. They were both, those neutron stars were kind of in the middle of the neutron star range. The resulting object is in the mass gap, and we don't really have good evidence for what it was. In this last run, 03A, whose full catalog should be published probably within the next month, we had another event published that was most likely a binary neutron star merger, most likely based on the masses. They fit exactly in this neutron star range. But in this case, we don't expect the axis of the merger to be pointing towards the Earth. So we didn't see any electromagnetic counterparts from this event, which was also further away. So in this case, there are still many more questions about what the constituents and what the remnant is. But we're definitely starting to populate this lower mass gap. And in addition to all these stellar mass black holes kind of between the 10 to 80 solar mass range, we also have some exceptional events with exceptionally low constituent masses. So this event here, GW 190814, which was published individually, had a very, very exceptional mass ratio of about 9 to 1, which means we know that the the heavy constituent had to have been a black hole. It's in the kind of in the mass range where we don't expect any matter to be sustained as a compact object. But the secondary object, the mass fits exactly in this mass gap. So we see it's above every known neutron star, but below every known black hole. So it could be either one, it could be something else. It's exactly the mass gap, and it's kind of this question mark object, which means we don't know what it was, and we're just starting to measure this new population of objects. Also here on the top, 1905-21 is the heaviest binary merger that we've measured to date. So heavy that one of the constituents, the primary constituent itself, was above what we believe to be the higher mass limit for a black hole. I should qualify that. Black holes can be of any mass. We talked about millions of solar masses in black holes. But to get a black hole as heavy as that from a star, we need some process by which a heavy star can live out its life and then end it as a black hole. And for stars heavy enough to produce a black hole of 80 solar masses as a supernova remnant, the original star pre-supernova would itself have to be unstable to parent stability, and we don't expect stars to form and be sustained in that region.
Hey, Ofek, there was a question in the chat about the x-axis of this figure.
I said that originally. It has no meaning at all. There's no meaning to the x-axis. It's just for spreading out the artistic representation, so they don't fall on top of each other. Okay, so this top triple is again interesting. The right object, the object on the right, the primary, we believe itself to be a result of a previous merger of two black holes. So we expect this to be representative of a dense cluster or dense stellar environment where many heavy stars exist, many of them collapse into black holes, and then they dynamically form systems by which a couple can merge. A heavier black hole would form not directly from a star, but a second generation black hole forming from two previous ones. And then the kicks, natal kicks that these objects have when they form by the mergers would cause them to kind of ping pong around in the cluster and undergo secondary generation and third generation, multiple successive mergers of black holes. And in this way, we think it's possible to populate higher and higher in this mass scale of heavy stellar mass black holes.
Ofek,
Yes.
can I ask a question?
Yes.
It seems that these merging events, at least the ones you can see, are kind of bound. It's not clear to me why very, very heavy, like these million solar masses, black holes don't also sometimes merge. Or why don't you see a continuum of much heavier objects?
That's a selection effect based on the detectors. First of all, supermassive black holes, like the ones in the center of our galaxy, do merge. They merge when their host galaxies merge. And we know that galaxies merge. Hubble released an image just this week of two galaxies merging. It's one of tens of images of merging galaxies. This happens everywhere in the universe. And when galaxies merge, eventually their center black holes will sink in the mutual gravitational well into each other and merge with the gravitational wave emission process. However, because their masses are millions of times the solar mass, that means that from a Keplerian calculation, you can find that the orbital period, the typical time period for these mergers, is not seconds or milliseconds, like for LIGO black holes. It could be months and years. For months and years, you need a detector that has resolution, the microhertz to maybe millihertz frequency range. You can't build something like that on the Earth. The Earth has a lot of seismic activity below approximately 1 hertz. So the Earth-based detectors are blind to these events, which is why there's a project to construct space detectors, such the leading one being LISA, the Laser Interferometric Space Array, and that's designed to detect supermassive black holes merging in the universe when galaxies merge. So the continuum here is, we don't know what happens between about 200 solar masses all the way to millions. We don't know if objects exist there, and we don't know, and can't see them merging with detectors yet, but we at least know that for supermassive ones, they do merge. We see the galaxies, we see them hitting each other, but we'll need to wait about a decade before the gravitational wave space detectors are able to resolve that, those signals. Okay. This catalog now is a bit old. It's still the latest published to date with the O3A catalog, which will be the Gravitational Wave Transient Catalog 2, expected to be published in about a month. But this shows the events that were published up to about 2 years ago, the 10 original binary black hole mergers. Here on the left is the famous one, GW 150914. 10 binary black hole mergers. You can see again for the time scale that it runs on less than a second for these typical masses of binary black holes of stellar masses. The corner one here, the longer one on the bottom right, is the binary neutron star merger, which we mentioned 170817. Because here the masses of neutron stars are about 10 times lighter than typical black holes, you expect the relevant time duration to be about 10 times longer. And again, and indeed here you see lower frequencies and a very, very long in spiral trajectory. Nothing to limit its stability. We expect black holes to be stable, and we expect their merger to produce a stable black hole. So there's yet no limit on the upper mass of black holes produced in mergers. We only think there might be a lower limit on a black hole mass mathematically. That would be when quantum gravity effects start dissolving the horizon. That would be the Planck scale, and it's very, very small. It's larger than subatomic particles, but it's order of kilograms, not order of a star. So we expect that to be a mathematical bound. For stellar black holes, we expect the lower bound not to be a mathematical one, but one of production processes. That is, we expect light stars not to be able to produce the density required to actually compact them into a black hole. The sun, for example, as a black hole would need to be about 3 kilometers in radius, and we don't know of any physical process which would condense and compact the sun into such a small radius. We don't expect the sun ever to become a black hole. Okay, Asaf said basically what I said. Why can't we measure gravitational waves from merging into supermassive black holes? To Mao's question, like I said, LIGO is not sensitive to the frequencies involved in the merger of supermassive black holes because the frequencies are much lower, the time scales are much longer. LISA would be sensitive to that, and we expect LISA to measure them. Okay, we have a short video now of the events we just saw. This is what they look like in simulations. Typically, we have two objects represented here by the little marbles circling around each other. We see that they faster, closer and closer. The gravitational accelerates in frequency. Frequency goes up. This is what we call a chirp. And this so eventually the new black hole that forms, which is highly perturbed and unstable, decays into a stable remnant spinning black hole, a Kerr black hole. Okay, let's go back to the presentation. Did I miss any questions? Okay. So what are these gravitational waves and where they come from? Where does general relativity come from? The specific math might be hard, but conceptually it's actually quite simple. We start with our best friends Isaac Newton and Johannes Kepler here. Represented on the right is a trajectory of a planet around the sun, but any two-body gravitational system would look the same. We know that orbits, like Kepler, should be ellipses on a plane. And we have this relation between the mass, the orbital frequency, and if it's a circle, radius, if it's an ellipse, the semi-major axis, or the distance that these objects trace out in their orbits. Newton, of course, explains that these trajectories are a result of a simple universal law of gravitational attraction, which is inverse to the radius to the distance squared and directly proportional to the masses. This is 17th century physics, and today taught in every first semester course. In second semester physics, we learn 18th century physics. We learned that Coulomb's force for electrostatic potential looks exactly the same. We replace the masses with charges, but the inverse square law is the same. And we have this minor subtlety of it being either repulsive or attractive, while gravity is only attractive. That's the minus sign and the sign of the charge. We also learn in second semester physics that Coulomb's force is actually an approximation for the static limit of what truly should be described with the four Maxwell equations, which describe not an instantaneous force at a distance between separated particles, but two fields, the electric and magnetic field, or if you pack them up together into a four vector, the electromagnetic field, which obeys a partial differential equation, which is local. So we have differential operators, divergences and gradients and autols or curls of vector fields. And at every point in space, we can relate the differential behavior of the field to whatever matter, in this case, electric charge density or electric charge currents are in that point of space at that time. Packed together into a compact form, we have this box operator, the D'Alembert-Sian, or the wave operator, which is basically saying that you can pack up all of your differential field operators into a single second-order differential operator on the left, acting on your field, in this case, a vector field. And you can pack all of your sources to the right-hand side. In this case, J mu, charge and current density. And of course, a result of this formulation and of this box operator being a wave operator, the result of that is electromagnetic waves. There are wave solutions to this equation, and that's the light and radio and whatever we use every day and see every day and listen to. And electromagnetic radiation is the result of changing Coulomb's law from action at a distance between charges to a differential equation which mediates the interaction between two particles with the field everywhere in between them. This should be familiar, 19th century, second semester physics. Einstein is really, and his greatest achievement was to unify these two separate fields, or basically to bring gravity back into this language of fields and differential operators, which are local and therefore obey relativistic restrictions like causality and propagation velocity for information, by expanding this force, or breaking apart the gravitational force, into a resultant effect which comes from a field acting on matter and produced by matter. So Einstein's field is not a vector field, it's a tensor field or a matrix, G mu nu, which is called the metric tensor, or Einstein's gravitational tensor, the field. Einstein's metric tensor, I should say. The equation that this metric tensor obeys is represented by Einstein's tensor, G mu nu, which is basically a geometric composition of derivatives of this tensor, this metric G mu nu, on the left-hand side. On the right-hand side, we have T mu nu, which is the stress energy tensor, or the content of space-time. This would include matter particles, energy, electromagnetic fields, anything that's not gravity, we would put on the right-hand side, and it would both be a source for gravity, because mass, we know sources of gravity from Newton. Energy and mass are relativistically interchangeable in a sense. So energy would also gravitate or produce gravity. The sources would appear here on the right, and the field affected by it would be on the left, appear on the left. Simultaneously, of course, the field would affect the matter, the content, and so mass, in a sense, would curve space-time, and that space-time would cause other masses to travel on curved trajectories. So Einstein explains gravity not as a force, but as a geometric effect created by matter and affecting matter. But even without going deep into what this equation looks like, we can kind of linearize it or find a solution in vacuum, or a solution that's with very small perturbations. And we mark those perturbations with a tensor H, which is our strain tensor. And we find that it actually obeys the exact same form of the equation, the same differential operator equation as electromagnetism. So this box operator acting on the gravitational field H alpha beta, or H mu nu, depending on how you want to label the indices, would have a wave operator on the left-hand side, and stretch energy or mass energy and sources on the right-hand side. The results of these formulations by Einstein, one of them we already mentioned, the precession of Keplerian orbits due to the relativistic correction, if you want, to the force of Newton. So that was known and demonstrated by Einstein over 100 years ago in 1915. The second result is that we have gravitational waves. Just like electromagnetic waves, if we can describe a linearized case of Einstein's gravity as obeying a wave equation, waves would have to be a result of that, and they would be carried away from a system which is in motion or in acceleration, more specifically that has a varying quadrupole moment. A binary system, a Keplerian system, actually has a varying quadrupole moment, which means a Keplerian system, a two-body orbiting system, cannot sustain an eternal ellipse, as Kepler and Newton has told us. It would emit gravitational waves. It would lose away energy, sink to lower and lower orbits, and as it does so, following Kepler's law, accelerate. And this is the in spiral, which is projected as a result, even without doing the calculations of exactly how much energy or what these field equations are. We can understand that every binary system in orbit has to decay in this way. It has to in spiral ever so slightly. Okay. Black holes today are also considered a prediction of Einstein's general relativity, but they weren't always, and they're not. And you can understand them even in classical terms. Mitchell and Laplace described the dark star, which is a star whose escape velocity is greater than the speed of light. That is, the star is both massive and compact, or very small, so that even light cannot escape away from its surface. For the sun, this comes out to be about the 3 kilometers, which we mentioned earlier, the Schwarzschild radius for the sun, equivalent to about 10 light microseconds. That's the light traversal time for a black hole as heavy as the sun. For stellar mass black holes, this number would be only slightly larger, and we understand that this number would basically determine the frequencies of gravitational waves to which our detectors are sensitive. If we get microseconds here, then we're talking about micro light seconds here, then we're talking about that wavelength of gravitational wave radiation and that frequency in our detector. Relativistically, one finds a black hole as a formal solution of Einstein's equation in vacuum when one assumes no change in time, a static space-time, and completely spherically symmetric. So completely the simplest possible case you can imagine of gravity, no matter anywhere, just spherical symmetry, and it's completely static in time. That's the Schwarzschild solution. And what would happen is this solution would bend the space-time around it so much that, again, light would have to travel on geodesics of this space-time, so straight lines on a curved background, which would look to us like curved space-time, like curved trajectories. And if they're close enough, then they cannot escape, which is why it would be a black object. More generally, we mentioned the Roy-Kerr solution, New Zealandic scientist who first formulated a slightly more complicated solution for Einstein's gravity in vacuum, a spinning black hole solution. This is a crucial one because stars generally do not have zero spin. Everything has some angular momentum, and you expect that angular momentum to be conserved whenever a collapse to a black hole occurs. So the Schwarzschild solution is really a mathematical isolate. It's just one point in the parameter space of possible solutions. But the Kerr solution is what you'd expect a star to actually collapse into. So this is a great discovery by Roy Kerr, followed by discoveries in the 80s of the stability of the Kerr solution. That is, finding perturbations to the Kerr solution, which means that if you perturb it slightly, it would decay into finally a stable remnant spinning black hole. So we expect all black holes in the universe to be of this type, of the Kerr type, a spinning black hole. And we hope that with images now coming of black holes in the universe, the first one famously here by the Event Horizon Telescope of the M87 galaxy, and we expect an image of the black hole in the center of our own galaxy, Sagittarius A star. We hope that as the resolution of these images improve, we'll be able to measure the spin and then really solidify that these are Kerr black holes, not just any dark compact object. And I hope that would be rewarded with a Nobel Prize to the Event Horizon Telescope team and to Roy Kerr himself. Yanni, I saw some activity on the chat. Is there anything?
Yeah, Ofek, you asked me to tell you at 11:30, so now it's almost 11:30. And Eli Balkei asks, what is a classical escape velocity of light given that mass of photon is 0, gravitational force is 0?
So classically, actually, in the late 18th century, they were not in the happy state that they didn't know photons had 0 mass yet. They were still debating the particle versus wave properties of light. This is before Maxwell's equations, before Maxwell explained light as a wave. So they just followed the Newtonian proposition that there are particles of light. Newton broke apart light in a prism to different colors, and he thought the different colors represented different particles of light, and he didn't know their masses, but whatever it is, of course, in gravity, the mass cancels out. You have Gm1, G big M small m over r squared equals ma, m cancels out, and so it doesn't matter what the mass of light particles are, they would still fall just like anything else in Newtonian gravity and in Newtonian light theory. So this is kind of a classical curiosity which could only be formulated at the end of the 18th century when they had Newton, but did not yet have the wave theory of light. And remarkably, it actually comes very, very, very close to the general relativistic properties, by which also you consider light trajectories on space-time. So now in Einstein's theory, you don't need things to have mass to bend their orbits. Space-time itself is bent, curved, and so the orbits, even of light waves, would be affected. Okay, we of course mentioned Penrose before. Penrose built on this Kerr solution and other results to claim that black holes were not only exceptional events, as I said, not exceptional solutions of Einstein's theory. They were attractors, in a sense, of the differential equation of GR. And so generically they would form, singularities would form, And according to his conjecture, the cosmic censorship conjecture, horizons of black holes will form around these singularities and hide the singularity from us, but provide us with a universe filled with black holes. Okay. A gravitational wave, as we said, is then a perturbation of space-time, of the metric tensor of Einstein, propagating through space and time. Because it's a matrix theory, the field is a matrix, we have polarizations of the matrix. We have two polarizations, plus and cross, which can be represented pictorially here, but are probably better, it's better to see them on this video. Here we have plus and cross polarizations in the middle. And you can see the pulsation going sideways for the plus, or side and up for the plus, diagonally for the cross polarization. For the circular polarization, which is a combination of them, you actually see the spinning of the system. And this is what we would expect to find from a Keplerian two-body system like the ones LIGO sees. The revolution of the gravitational masses in space would produce these waves. Here we see it from a side view, the wave propagating through space and bending space-time as it goes through in either the plus, cross, or circular polarization combination. This simulation, by the way, was produced here by Ofek of the physics department at Bar-Ilan.
There is a question, how come the classical term of escape radius is the same as Schwarzschild radius?
You can think of a few ways of, wait, this is now stuck. No. So, out and back. Okay. You can think of it as a coincidence or explains the coincidence. You can think of it as having more meaning. People argue both ways. For a spinning black hole, it doesn't come to be exactly the Schwarzschild, the classical radius. So it's kind of, you can't formulate a mathematical toy model which explains why it is the same. For Schwarzschild, it doesn't work for Kerr. So it's really up to people's personal preference how to think of them. Okay, I'm going to skip this video, which shows how the gravitational wave affects the detector. But we can use this illustration as showing that when you have masses on, for example, a circle, they'll be stretched either in a plus or cross repetitive polarization. And if you build an interferometer in the middle of the circle with the two test masses at 90 degrees from each other on the circle, then you'll have differential distances between the central beam splitter to both sides. And this is all that LIGO does, and it's all that LISA will do in gravitational waves today that are interferometric work exactly in this way. You build you bounce a laser between mirrors, and you measure the gravitational wave passing perpendicular to this plane of your detector array. We have the three LIGO and Virgo detectors represented on the left. Kagra is also now in operation. It's an underground detector in Japan. We don't have images of that because it's underground. And soon we'll have nice space images of LISA and other space detectors. Okay, this is slightly more mathematical, but it only represents what we mentioned before of how gravitational waves are produced by two bodies which orbit each other in a Keplerian-like system, radiating away gravitational waves by this quadrupole formula, which is the equivalent in gravity of the electromagnetic Larmor formula, which people typically study either in electromagnetism courses or when they study the problems birthing quantum mechanics with the instability of an atom, because it would have to radiate away dipole radiation electromagnetically. So this is an equivalent of that when you work it out from the field equations of Einstein. The exact term doesn't matter to us too much, except that we realize it has to radiate away gravitational waves, taking away energy as the system moves. Then the objects would sink closer to each other to lower orbit, or to deeper down the potential well that they create for each other. Obeying then Kepler's law and Newton's laws to first approximation, they would rotate faster because two objects of the same mass the closer they are to each other, by Kepler's law, would orbit faster, so the frequency would increase. This would again increase the production of gravitational waves, accelerate the energy emitted from the system, the power emitted from the system, cause them to come closer even faster. And this is, again, the typical chirp process that we see. The amplitude grows, the frequency grows, until eventually they merge. If you follow the math, you find this chirp mass relation, which describes just how fast this process happens. And it depends directly on this mass combination, mass scale with particular powers of the two separate masses. This was already actually observed before gravitational waves were directly detected by LIGO in the 1980s. Halson-Taylor found a binary pulsar or a binary neutron star, and it was traced by Taylor and Weisberg throughout, at that point, the late 70s and early 80s, and they found that the period actually changed with time. The period became shorter and shorter, the frequency grew. It's now been projected and followed over about, in this plot, about 30 years. By now, it's already been more than 40 years of following this system. And they found that this does evolve exactly according to general relativistic predictions of energy loss to gravitational waves. And they were actually awarded the Nobel Prize for this detection in 1993, meaning that gravitational waves indirectly have been a solid and observationally established aspect of general relativity and astrophysics for almost 30 years now. We've seen them and we know that they exist. It was still open to measure them directly. And the problem why it was so hard to measure them directly, other than the signal being very small, is that you need to know how to construct and how to follow the system and the signal throughout the evolution of the system. In this cartoon by Kip Thorne, it kind of tried to demonstrate the problem. We know the early stage of the evolution of the system. This is an in-spiral, and you can solve it in almost Newtonian terms or minor modifications, which are called post-Newtonian modifications, but you can only follow it so far. On the other hand, you know what a perturbed black hole looks like. You have an equation. This is the post-Newtonian derivation, and here on the right side is the equation by Shaul-Tukolsky from the 80s for describing the perturbations of a curved black hole on the ring down side. That is, the final object would decay to a stable stationary black hole with some quasi-normal modes which you would expect from any perturbed bell system or musical instrument system. It was this part in the middle where we really had no idea what would be happening. So Kip Thorne marked it as some squiggly lines which represent the mathematical or graphical equivalent of here be dragons. This is in the middle, it's a nonlinear system. Einstein's equation is nonlinear. Second order partial differential equation, very nonlinear. Anything could theoretically happen. And if you don't know exactly what happens in this regime, where the signal is strongest, so most of your signal is actually where you have the least ability to model it, you can't really hope to expect to find these systems with any confidence. It was a breakthrough in 2005 of numerical relativity, represented here, which showed that actually this merger is quite regular. It's not crazy, nothing very strange happens. We can follow, since 2005, follow an evolution of a binary black hole system from the in-spiral with growing post-Newtonian and relativistic effects well into a numerical solution of the differential equation with numerical relativity up until we can identify the ringing down of the quasi-normal modes following Tukolsky's equation. So this is what we expect a signal to look like. And here on the right, represented on a time frequency scale, and this frequency going up until it plateaus at the end of the process. Not surprisingly, or surprisingly but satisfactorily, this is exactly what we saw with GW150914. We saw the frequency going up as we expected, the amplitude going up as well. In the merger, we have the most signal until it eventually plateaus in frequency and kind of disappears in amplitude as the system brings down to its final steady state. Also represented here in this now famous plot of what the signal actually looks like with noise superimposed, or rather noise not yet eliminated, but we have this periodicity which becomes shorter and shorter. The frequency is increasing. The merger is very high frequency, and then some ring down at the final and peak frequency. And analysis of this DW5914 curve following the frequency and frequency evolution, so F and F dot, shows that the chirp mass, that parameter which determines the evolution, is about 30 solar masses. And if we compare this to the Keplerian calculation of how distant these objects would have to be objects of 30 solar masses orbiting each other at about 150 hertz or 75 hertz for the orbital period. It's half the gravitational wave frequency. You find that you can actually follow Kepler's law approximately until they were about 350 kilometers apart. The Schwarzschild radius corresponding to the system is about 200 kilometers, which means these two objects are orbiting each other as separate, distinct objects, close enough to be less than twice separated than the Schwarzschild radii, or the most compact they could possibly be. If we compare this to the 100 to 1,000 factor for the observations of S stars in the center of our galaxy, the Getz and Genzel discovery, we find that we're now about 100 times better in pinpointing that these objects have to be massive and compact and basically have to be black holes. So this is one of the confirmations of black holes, and again, one of the reasons and stepping stones for this explosion of black hole physics in the last few years, coming from all directions. We can now probe closer and closer to the horizons of black holes. After the merger, we can again probe the black holes very, very close to the horizon. We can find the ring down, or the final frequency and damping time of the modes coming from the black hole. This is an analysis of DW150914. And I won't go into all of it, but basically you can trace the frequency as coming from the light ring, or the potential barrier for light geodesics around the black hole. For a Schwarzschild black hole, the horizon is at 2 times GM over C squared. For light trajectories for the light ring, it's about 3M. So about 1.5 removed further than the Schwarzschild radius. The behavior of the gravitational well around there determines the potential for scattering of light waves from this black hole. And that's what we're trying to measure. Here, measuring one mode, we see there's a degeneracy in the resolution. But if one manages to see multiple modes, then one can pinpoint quite well what the parameters of this final object is. And while these plots on the right here from one of my papers from a few years ago was projecting that this would be, one could do this, we now have, with these 3 events published from the O3A catalog, we actually do measure higher modes or additional modes in the ring down, and accordingly we're pinpointing black hole parameters, masses and spins of the remnants, and properties of the birthing systems, the progenitor systems, better and better. We're really pinpointing these objects. We mentioned of these, the 1:9 mass ratio objects. We're really studying not only the chirp mass, the leading order effects, but we're probing higher and higher effects in these systems of black holes. Yoni, should I answer anything in the chat? Or
no more questions, but we have only a few minutes left.
Okay. So I'll skip the other tests of general relativity and area theorem, which we're doing with black holes, because I did promise to talk about the future. And this is the future. This is the very near future. It's a conclusion of the O3 observation run, the third one, which lasted almost a year. It was cut early because of the COVID-19 situation. But even while it was running, we see that we had excellent duty factor in observation time. So we had about half of the time triple detectors online, and almost 80 or 90% of the time at least 2 online. The ranges here represented in the different colors for the different detectors, we can see in all cases are much higher than the O2 ranges. So purple is above the previous purple, red is going up, blue is going up. We're expanding the horizon distance to which we can see these events. And we've announced to the community about 56 gravitational wave events, alerting astronomers that they might be interested in looking at these. Of them, only 4 have been officially published. We expect the full O3A catalog to come out, like I said, in about a month. And the full O3B catalog probably about half a year later. So we expect the diagram of black holes populating our universe to grow from about 10 to about 60. And we're mapping out those masses and ranges. The future is 04 and 05 for Earth-based detectors. We expect the ranges to increase even more. We expect LIGO India to come online as well in these years and have better localization of sources in the sky with triangulation with 4 detectors and not only 3. This is very important for multi-messenger astronomy, for being able to see binary neutron stars, for example, by looking exactly at where they are in the sky.
There's a question.
Space detectors are the next thing. Now I'm done.
There's a question in the chat. Can you talk about the possibility of tabletop detectors?
Not my field. There was some work on it. Okay, there was early work on it in the 60s. Joe Weber constructed. His idea was to do resonance bar detectors, so to measure gravitational waves not with interferometry, but with some sort of modes perturbed in a solid. That failed in an interesting way. He claimed that he built it and found gravitational waves. People then actually tried to repeat it or analyze his data and found that any reasonable physical source would be much lower than his noise levels. So he had to retract it. That result is no longer trusted. But it was one of the driving forces for theoretical calculations in the field. To prove him wrong, we actually had to get better estimates of waveforms and what waves would look like. So he's considered one of the founders in the field, even though his particular contribution turned out to be wrong. And in science, of course, the wrong results can be as important as the correct ones. Today, people are looking more into doing this cryogenically or with all sorts of superconductor systems, where they expect to have macroscopic perturbations and not just the technology Weber had. This is still in the future, but people are definitely thinking about it.
May I ask a question?
Yes.
What's the difference between black stars and black holes?
Black star is just the archaic term. It was used by Mitchell and Laplace in the 1700s to describe a star that was so dense light could not escape from it. It then fell out of use in the 19th century because in the 19th century we realized light has no mass and then thought it could not be affected by gravity. So we expected light to be able to leave any area. And then in the 20th century, it was replaced by the term black hole in general relativity. I think the term itself is from the 60s, where we actually, again, understand that light is affected by gravity, and you can imagine or visualize or mathematically describe a region of space-time whence light cannot escape.
Thanks.
Okay, I see a question about S2 and A star, which Asaf answered, way too weak. And we can understand this weakness if we recall that the compactness ratio, how close the system is to the Schwarzschild radius, is about order of 100 or 1,000. So you'd expect gravitational waves to be not only 100 times weaker than the systems that we measure, but actually some power of this factor of 100. And that power is about 5 or 6. So ridiculously small amplitude, no way we would expect that to be detectable in any reasonable scenario. Okay, any more questions?
I have one question. Is there a qualitative feature that distinguishes the chirp pattern of merging black holes as opposed to neutron stars?
Yes, we have not yet detected it, but there is. It comes in from, do I have it written here? I don't think I have a slide about it. Okay. So black holes are very clean systems in GR. It's vacuum, it's only geometry, there's nothing else there. So we can trace out the chirp and the perturbations to the chirp, the post-Newtonian and the merger effects, mathematically very easily, or relatively easily. Neutron stars have matter inside, and the matter is distributed according to some profile, which is related to the equation of state of the matter, the pressure, density, temperature distribution, processes happening inside, etc. Gravitational, magnetic fields, perhaps as well. All these things would experience gravity slightly differently, because if you're not dealing with point objects, but with extended objects, you have tidal effects, tidal forces. So like the Earth and Moon have a tidal effect, which means our trajectory gravitationally is actually not stationary. We're slowly drifting away because of tidal effects. Neutron stars would also tidally affect each other as they spin, and this would have a signature on the gravitational wave pattern. It would not be just a clean chirp. You'd have some measure of the tidal effects also coming into interaction. One affect one with the other, and then you'd have everything. You have spin-spin couplings, spin-orbit couplings, different tidal multiples can behave differently. All these different effects would come in, and it would make the in-spiral slightly more complicated. But with enough SNR, you can hope to measure it. So until now, LIGO and other groups have actually published bounds on what's called the love numbers of tidal effects in neutron stars. That is the relation between the tidal field applied to a neutron star and the response in quadrupole moment in the neutron star, dipole and quadrupole moment. So, if I take a piece of rubber and I squeeze it, it would react in a certain way. A metal would react in a different way. Now we can measure the reaction of a neutron star to gravitational tidal forces applied to it based on these gravitational waves from merging neutron stars. But we only have one, and it's a very weak effect. So the bounds are not very strict so far. I don't think we managed to rule out equations of state based on the tidal effects yet, but we're getting there. The increase in range represented here, you can think of as either seeing a low source further away, or as seeing the same source closer and then with more signal. So with more signal for sources like 170817 and with better sensitivity, we can hope to better measure these tidal effects and love numbers and kind of probe into neutron stars and their inner structure.
Ofek, many people have to start teaching, so maybe you can finish and then we'll leave the session open for more questions, whoever wants to stay with you.
Sure. Then let me just go to the credit slide for the LIGO, this slide here. And with this, I am done.
Okay, is there more questions? Because I have a question. So, the second event with the merger of the two neutron stars that was observed really, there was a trigger by LIGO and then observed by many other telescopes. Has there been more events like that happening? I didn't get that.
There was no other event, like confirmed event like that. the event you're talking about is 170817, the binary neutron star event, and here we have a summary of all the observations by different telescopes and spectra ranges following that event, starting from the LIGO Vertigo detection of the chirp and gamma ray, X-ray, later UV optical, all of the electromagnetic radiation that was found from that event. That was a great event because we had 3 detectors on at the same time gravitationally to see it, which means we could find the location in the sky to a very good accuracy, a very narrow region of error. And we can match it up with the host galaxy and with electromagnetic observations at the time. We expect this to happen more and more with better sensitivity of the gravitational wave detectors, and also with the LSST telescope, which will have the capacity to rotate and to point very fast in a very short response time to a LIGO Virgo trigger of a gravitational wave event worth looking at. But there's a caveat, there's a problem here, and that is that most of this energy emitted in electromagnetic spectra is very highly beamed in the jet of the binary neutron star merger, the gamma ray burst, or in other effects. You typically only see the afterglow a long time afterwards in spherical symmetry. The bulk of the energy, the most interesting part of the observation, is very strongly directed. And if you're not lucky enough to have the jet pointed at you, you'll most likely miss most of the most interesting part of it. So in the beginning, I showed this this question mark event here on the left, GW 190425. We think, like I said, it's a binary neutron star event because the masses match neutron stars, but we didn't see any electromagnetic counterpart. Now, it could be because they were not neutron stars. It could be because it was too far away. Most likely, you didn't see anything because it just wasn't pointing in your direction. So we're still waiting not only for more binary neutron star events, but for more binary neutron star events which happen to be pointing in the right way towards the Earth.
I have a question, very quick question.
Yep.
What's the timeline for 003 publication, 04 and 05?
03A, the first half of 03, the paper is written. All the companion papers are written. They're in final circulation and management approval. I expect them to be published, if not within the next week, within the next month.
Okay.
That's 03A. 03B was nominally supposed to be 6 months later, but with COVID-19, all timelines are kind of pushed. 03 was actually cut short by a month because of the situation, and all the timelines have been stretched. So 04 is probably going to be delayed a bit, and publication of 03B
this spring. No? No.
Okay.
My system froze.
No, I can still hear you, Asaf.
No, I stopped hearing Ofek.
Yeah, I think Ofek logged off. Like accidentally, probably.
I guess maybe this is a sign that it's about time for us to
Yeah, perhaps.
stop the meeting. Oh.
Like I was saying, I would bet 03B to be published in the first half of 2021.
Okay, and then 04 and 05?
I think the current agreed deadline with NSF is 18-month cadence after the data taking is complete. So it's a question of whether all four would run as a single segment and be published at once, or if it would be also cut into either half-year interval or 1 month intervals, and each of them would be published with an 18-month cadence, which might be lowered to a 1-year cadence, depending on however those politics go. But you'd have to wait for it to start first, and we don't know exactly when that would be as well.
Great, thank you very much.
Thank you. I enjoyed the talk. Bye-bye.
Thank you all for coming.
Bye.
Ronnie, if you want to leave the room open so people can ask me questions. If not, I'll gather my students and we'll go.
Thanks, Ofek. Bye.
Thank you.